And contacts. There's always lots of updates in contacts. So I've trimmed it down to the most relevant stuff. And the one that is most relevant to most people is the default behavior of bonded contact. That's transitioned from augmented Lagrange into MPC, so constraint-based contacts. Lots of reasons for this. It gives more accurate results, contacts with gaps. So if you have two bodies in contact bonded with an air gap between them, MPC contact will transfer loads much more accurately than augmented Lagrange. Much better convergence behavior, no penetration, rigid body motion, other things. It gives much better results. So for example, here's a result with augmented Lagrange bonded contact. This is using the beam formulation, which is computationally expensive, but quite accurate. And then this is the MPC formulation. So you can see MPC and beam are virtually identical, and augmented Lagrange in this case is way off. Augmented Lagrange works most of the time, but there are a few cases where it's just not as accurate. Here we have a pipe bolted to a flange, and you can see you get these spurious stresses around here with this augmented Lagrange approach. With MPC, much more smooth, realistic stress distribution. There's a few exclusions for MPC where it will automatically switch to augmented Lagrange. So thermal, acoustics, and coupled field analyses, it's more appropriate to use augmented Lagrange. Cyclic symmetry, structural optimization, additive manufacturing. So yeah, basically user beware. It's going to be MPC unless you're using one of these special cases. So maybe just check to see what it's doing. With MPC, however, because it's constraint-based and not penalty force-based, you can't get things like contact pressure or frictional stress, sliding distance, or contact forces from it, because the data just doesn't exist in the analysis. So if you do need those sorts of results, switch it over to augmented Lagrange to get those results. One downside with MPC contact is the chance of having an over-constraint. So if you have overlapping contacts, you get multiple constraints generated and you get possible over-constraint happening. So there's a new feature or new option, or this aspect of the contact tool that will tell you if there's a possible over-constraint, and we can insert this tracker that will flag a possible over-constraint. So if it comes up as a -1 here, it's saying possible over-constraint. Maybe check how your contacts are defined, especially those pesky automatically defined contacts that creep in everywhere. Check those, make sure they're not overlapping and over-constraining your model. Adaptive element removal. So this is an enhancement of the smart remeshing capability. So smart, we present it every time we do these updates because there's always some cool changes in the smart remeshing for things like rubber seal analysis or forging, anything like that. So now there's this enhancement where we can remove elements based on some failure criteria and allows us to introduce some sort of failure behavior that normally we would have to go to explicit analysis, like say LS-DYNA, to do this sort of thing. So at the moment it's only 2D, but I'll show you some examples of where we might use it. So here's a thermal expansion, and you can see the elements get distorted or you get material failure, so you get element deletion. Here's breakage of a lattice structure in tension, and snap, there we go. So you can see the elements are failing and breaking. And normally this is a very difficult thing to do in implicit analysis, and we would use explicit for it. But there have been lots of enhancements to the contact behavior. So the newly revealed surfaces, when you delete the elements, now you've got new element faces that have to be involved in the contact. So there's some enhancements to the contact that allow that to work better. So you can get these piercing models. So if we zoom in there, you can see here how elements are getting deleted based on a failure criteria, and this needle or whatever it is continues to pierce through the newly revealed elements. A few more examples, some plastic necking, plastic necking with a hole. There we go. Want to generate your own NLAD Ansys logo. Someone has way too much spare time. This is a nice one. Pull out of a pin. So like a metal pin bonded to maybe a rubber material, we pull it out and it causes tearing in the rubber material. And then finally, we can do like a basic wear simulation. So we're calculating the wear effects here and deleting elements based on the wear. The other way to do this sort of wear approach is with a remeshing process. So rather than deleting elements, you'd morph the mesh. That's a more accurate approach, but a bit more computationally expensive. Structural optimization. There's always lots of stuff happening here. Structural optimization is really the overall tag that's applied to all these optimization methods. It used to be just called topology optimization, and then they introduced all of these extra capabilities. So now it's just structural optimization, and then there's all this other stuff that happens below. So we have this new mixable density algorithm, some enhancements to the level set algorithm in the topology optimization, some changes in the free morphing, which I'll show you. The density method for optimization was the default. So there's some enhancements to that to make it the mixable density method that allows it to be combined with other topology optimization methods. That's why it's called mixable. So we can have results based on displacement, velocity, and acceleration, as well as stress, as you'll see, and then they can be used as objectives or constraints with this mixable density topology optimization approach. So stress criteria is now supported. So we can have like a minimum compliance based on stress, and then also have our mass constraints to generate our optimized design. So in this case, we're minimizing the von Mises stress using the mixable density solver. So that's topology optimization, where we take a big block and we ask the solver just to remove material until we reach, say, the mass we're after. And the other approach is shape optimization, where we give it the shape that we've come up with and ask it to improve it for us by basically morphing the shape. So we're changing the outer boundaries. And this has been enhanced with this extrusion constraint. Apparently this came from watchmakers. They have these little parts that they make with extrusion processes, and they want to improve them so we have fewer stress concentrations and generally make them more robust. So the shape optimization can morph these parts to reduce the stresses, but also make them still manufacturable using an extrusion process. So that's what this new capability gives us. A few other things in the topology optimization, and shape optimization, enhanced accuracy and speed. So with the shape optimization, what took previously 40 iterations now takes 20 iterations. Using the level set-based topology optimization solver, what previously took 70 iterations now took 25. So these solutions are quite long duration. They do take quite a while to solve, so that's a really big improvement. There's also this new complexity index. So topology optimization will often give us these weird alien-like structures, which are not manufacturable. And this complexity index allows us to simplify things and give us something that is a bit more achievable. So it's a simple parameter that we set between 1 and some higher value. 1 will generate a sphere, or higher values will generate more complex structures. So this is the same analysis solved with complexity index of 3.5, 2.5, or 2. And as you can see, it's getting simpler and simpler and more easy to work with. For topology optimization for modal analysis, something that can happen here is as we change the shape of the design, the modes and frequencies switch over. So what was previously the third mode now becomes the fourth mode, and that becomes pretty difficult to for the optimization process. But now there's improved tracking, so it's able to work out, or it's able to track the particular modes as they swap around. And so when we tell it that we want certain frequency to be minimized for a particular mode, it's able to track that mode as it switches around when the geometry changes. There's also this new option for minimizing or maximizing compliance. So most of the time we want to make structures stiffer and stronger, but sometimes we want to make them more flexible. So now we can maximize compliance. So for example, here we're asking the solver to give us a more flexible structure. So we still want to keep the stress down, but we want the thing to be able to deform a little bit more. So yeah, we can do that with the topology optimization. And then similarly for thermal compliance, you can minimize or maximize that. In this case, it's giving us, we've wanted to basically make it a better thermal insulator, and it's done that by just carving a hole right through the middle. Probably not the result we're after, but the computer says it did its job. And also, topology optimization works with condensed parts now as well. So if we have some complex structure with multiple bodies, and we only want to run the topology optimization on, say, these two bodies here, what we can do is we can use condensed parts or component mode synthesis to represent the other bodies. So we get the stiffness and the deformation response of these structures here, but they're represented with a super element rather than the entire mesh. And that just speeds up the whole solution because we've reduced our mesh size overall.